In calculus, space is strict. Every point sits on a rigid grid, and the distance between any two locations is exactly measurable. But if we strip away that grid, we enter the world of general topology, a space defined entirely by relationships, where objects can stretch, morph, and bend without any concept of distance. This standard definition of a topological space relies strictly on a collection of subsets called open sets. It's a broad definition that permits bizarre, unmanageable spaces. For instance, as shown here in the discrete topology, every single possible subset is open. When every subset is open, or almost no subsets are open, standard mathematical tools fail. To do meaningful mathematics, to take limits or approximate continuous functions, we must impose structural constraints that limit the size and behavior of these open sets. Without these constraints, analytical intuition regarding how sequences behave breaks down. In a standard coordinate plane, a sequence of points converges to exactly one destination. But as James Munkres details in this text, in an arbitrary topological space, a single sequence can simultaneously converge to multiple distinct points at the same time. To maintain consistency, topologists developed a hierarchy of constraints. We are going to map the four major countability and separability axioms that force these wild topologies to behave. By mastering these four axioms, we gain the structural blueprint needed to build a bridge from shapeless spaces back to the well-behaved geometry of the real world. We start with the strongest constraint, which relies on the concept of a basis. A basis is a subcollection of open sets that can be joined together to generate the entire topology. In a standard metric space, the basis consists entirely of open epsilon balls centered around points. Any open set in the space can be built just by taking unions of these simple balls. A space is second countable if it has a countable basis. Every open set is generated from this countable list. In Euclidean space, we construct the coordinate plane using only rational coordinates and radii. Thus, second countability acts as the top-level filter in our hierarchy. This is a significant global restriction. It ensures that the bulk of the topology structure can be cataloged using a countable amount of data. We can also scale our constraints down, shifting focus from the global structure to the local environment surrounding a single point. A space is first countable if every point has a countable local basis, described by a sequence of shrinking neighborhoods. This means every second countable space is automatically first countable. The subset of global basis elements containing a point forms its local basis. First countability provides a crucial analytical guarantee. If a point is a limit point, a countable sequence of points converges directly to it, restoring standard calculus intuition. There is another way to constrain an infinite space, counting a framework of reference points embedded within it. In topology, a subset is called dense if every open set in the entire space contains at least one point from that subset. A space is separable if it contains a countable dense subset. For example, countable rational numbers are completely dense within the uncountable real line. Through closure, these rational anchors mathematically generate the continuous real line. Because of this, second countability implies separability. Separability ensures we can approximate any unknown irrational point using a countable sequence of known reference anchors. Our final axiom involves open covers. A cover is a collection of open sets whose union envelops a space. It allows topologists to prove theorems about infinite spaces without checking every single point. The highest standard for an open cover is compactness. As defined in the text, a space is compact if every possible open covering can be reduced to a strictly finite subcollection that still covers the space. Since many spaces aren't compact, we use the Lindelof property, meaning every open cover contains a countable subcover. This completes the downward arrows of our model. Any space with a countable basis is automatically Lindelof. The Lindelof property is a safety net. It guarantees an unmanageable cover of an infinite space can always be reduced to a countable sequence. We know a second countable space is automatically first countable, separable, and Lindelof. But do these logical arrows reverse? If a space is first countable, is it automatically second countable? In general topology, the answer is no. We can look at the uncountable set equipped with the discrete topology. This space is first countable. Because every individual point forms its own open set, it acts as a finite local basis. But it fails the other axioms. Because every point is isolated, any global basis, dense subset, or cover requires uncountably many sets. This proves that second countability necessitates these other properties, but the inverse is not true. While second countability remains the primary indicator for all other properties, the weaker axioms remain distinct and independent in the wilder regions of general topology. We have navigated the abstractions of topological spaces, but what happens when we reintroduce a distance function and return to metric spaces? Inside a metric space, the fragmented rules of countability align. Under the constraints of a metric, second countability, separability, and the Lindelof property become mathematically identical. If a metric space possesses just one of these three properties, it possesses the other two. This complex hierarchy of countability axioms exists because general topology lacks the unifying structure of a measurable distance. Why identify these separate properties if they collapse into equivalence in familiar spaces? Identifying these properties is exactly how mathematicians prove that an abstract space can be turned into a familiar metric space to begin with. This leads to Urysohn's metrization theorem. It establishes that second countability is the mandatory architectural requirement to define distance on a regular space. Countability axioms provide the structural requirements to bring a wild, shapeless topology into the measurable world of geometry and calculus.